Okay, let's get started. Hope everybody is doing well. Your next homework assignment is due a week from today. I've just handed out the paper copy of that. It's also posted on Blackboard. Today we're going to move from Chapter 7 and into Chapter 8. I'll again suggest that it would be a really good habit to review the textbook because I think there's some important information there that sometimes we don't have the chance to go through everything. I think, for example, you had a homework problem that asked you about the SING criteria, and hopefully you were able to find that right there in the text or maybe using the index. There's just a handful of topics where there's not enough time, so I think it's valuable to supplement what I tell you through reading the textbook. So today's material is sections 1 and 2 out of Chapter 8. We're going to learn about some ways to determine F value besides using the Moody diagram. I'm going to teach you about the Colebrook equation, the Jain equation, and then apply all of that into a process that we can use to size required pipe diameter. Any questions before we get started? So you remember the Moody diagram, and something we haven't talked much about so far is that across the top here you can see how it's distinguished between the rough turbulent zone and the transition zone. And we'll get into that more and what it means, but it's related to the boundary layer thickness relative to the laminar sublayer, and which portion of two factors is dominating the friction factor. And we'll see these two different components of what determines the friction factor when we look at the Jain equation and the Colebrook equation. So here's the Colebrook equation. If we want to find the friction factor F, if conditions are laminar, you can just have 64 divided by the Reynolds number. But that's going to be very uncommon, that we have laminar flow through the entirety of a pipe. So in other conditions outside of this Reynolds number range, the Colebrook equation applies. So this is an equation to solve for F, but it's what's called an implicit equation, which means that the unknown you're trying to solve for is in multiple locations in the formula. You'll notice that if we're trying to solve for F, it's on the left side of the equation and the right side of the equation. And you could do algebra all day long, and you're not going to be able to isolate F on either side of that equation. So what you have to do instead is a trial and error approach, where you assume a value for F, and then you see if the left-hand side and the right-hand side equal each other. So you can use an equation solver on your calculator to solve for F, or you can set it up with Excel, and I'll show you how to do it that way. Now, remember that what F is determined by is you can see that the relative roughness is one of those terms, so the ratio of K sub S to D. So that was this part of the Moody diagram. So that's one of the two things that determines the friction factor. So this first term that's inside the logarithm is the relative roughness term. And then it also depends on the Reynolds number. And so that was this part of the Moody diagram. So it was the combination of relative roughness and the Reynolds number that determined the friction factor. Seth, any questions so far? No? Okay. So what we do is we substitute in the known K sub S, the known diameter, the Reynolds number, which comes from the flow conditions, and solve for F. Now this is implicit, which means it's tricky to solve, especially if we're having other components of iteration within our process. So it's best solved on the computer with a good calculator, and we can get those equivalent sand roughnesses from our textbook, other books. I think this is a table that comes from the fluid mechanics book, but our textbook has them as well. And you'll remember that sometimes it's designated as K sub S for the equivalent sand grain roughness. Other texts label that as epsilon, but it's the same thing and the same values. regardless of whether epsilon or K sub s is used in the formula. So just to show you what the Colebrook equation looks like and how you could solve it with Excel, let's take a look at this example. If we had a pipe that's 136 millimeter diameter, and it's galvanized iron pipe, so we could look up out of the table for galvanized iron. See here, galvanized iron, 0.15 millimeters is the K sub s. And when the 200 liters per second is flowing through that pipe, then we want to use the Colebrook equation to determine what is the friction factor for that pipe. So the first thing I'm going to do is calculate the Reynolds number, because that's one of the things that's going to go in to our formula is the Reynolds number. And so I might as well just do this whole thing on Excel, since we're going to be using Excel. All right. So let me put in the flow rate, Q, in terms of cubic meters per second. So that would be the given 200 liters per second divided by 1,000. So 0.2 cubic meters per second. That's the flow rate. And the pipe diameter is 136 millimeters, and so then the diameter of the pipe in meters is 0.136. And the reason why I need to know the diameter is to get the area of the pipe in square meters. Okay, so the area of the pipe is going to be pi d squared divided by 4. So pi times d squared divided by 4. Okay, so that's the pipe area, and then from that we can get the velocity in terms of meters per second. So V is Q divided by the area. So the water is flowing through that pipe at 13.7 meters per second. So it's moving along at a pretty good speed. And now from that, we're going to determine the Reynolds number. And let's see, it says here the kinematic viscosity 1 times 10 to the minus second, 10 to the minus sixth meters squared per second. Okay, so kinematic viscosity, meters squared per second, 1e minus 6. Okay, so then the Reynolds number is velocity times diameter divided by kinematic viscosity. So that gives me the Reynolds number. So that is going to go here into the Colebrook equation. So the formula that we're going to use here, let me paste in Colebrook equation. So we have the Reynolds number. The problem statement told us the K sub s of the pipe is 0.15. Let me put that in. K sub s in terms of millimeters is 0.15. Now, we have to have the same units for K sub s and for D. So I've got the diameter here listed in meters. Let me also get the diameter in millimeters, just so that I am sure to use the right thing when I put it into this log function. So diameter in meters times 1,000. Okay, so I think we have everything we need to start substituting into this formula. So I'm going to have the right-hand side of the equation and the left-hand side of the equation. And I have to start with a guess value of the F value. So this is like a guess F. So is it 0.008? And why did I use that number? Well, if we look here at the Moody diagram, the bottom of the Moody diagram is 0.008. That's the smallest you're likely to see for an F value. And the biggest you're likely to see is 0.038. So what I'm going to do is I'm going to say 0.8, 0.009, 0.01, and kind of take it in steps to see if the left-hand side and the right-hand side are equal. And so I also want to have a difference, because left-hand side and right-hand side should be equal when the F value that's being guessed is correct. So we want, our objective here is for the difference to be equal to 0 for the correct f value. Okay, so the maybe I should switch left-hand side and right-hand side, because I'll start with this left-hand side first. So 1 divided by square root of f, sqrt of f. Okay, so if the f value is 0.008, then that's the left-hand side of the Colebrook equation. The right-hand side of the Colebrook equation, have to be careful to get it right, parentheses count here, so equals -2 times the log of k sub s divided by 3.7d. So I'm going to say k sub s in millimeters, anchor the reference, divided by 3.7 times d in millimeters, and anchor that reference. Okay, so that is the first of these two terms that's inside the log, and now I'm going to add 2.51 divided by the Reynolds number, anchor the reference, times the square root of f. All right, and one more. I think I've closed it now. Oh, one more. Now we're done. So this is the right-hand side of the equation if the f value is 0.008. So they're not equal yet, but we can calculate the difference, one minus the other. And I could either have it going in increments of 0.1 and then fill all of these as well. And we want to find out where is that crossover point. So we're pretty close. 0.02 is too big. 0.021 is too small. Of course, probably you're already thinking of goal seek, right? You're thinking, what if we say data, what if analysis, goal seek, and you're saying okay, so we want to set that to 0 by changing the f value. And then that's going to tune us in just that little bit extra to get the perfect f value. And we could show more digits here to see that it's exactly 0.02027 is the f value that applies here. So that's the Colebrook equation to find the f value. Now, that's maybe not any simpler than just using the Moody diagram, right? But at least now it's based on an automated process that doesn't require you to get your finger out and follow and trace like a figure, because this could be automated and worked into a spreadsheet solution, whereas having a person, a human, look off of a graphical figure can't be automated in the same way. Okay, so that's the Colebrook equation. Now you could put it into your calculator. Maybe if you've remembered the lessons you learned in Engineering 111, you could use your Casio to solve for f by typing this formula in. That's another approach as well. It'll take about 30 seconds to converge and to solve the equation if you do it on your Casio. I've got a little demonstration here where if you want to see what a real calculator would do, there's a video here. We won't take the time to watch it, but I really like the Hewlett-Packard calculator because it's got a much more powerful processor.
Our job is to make college easier because students have a lot.
It's too loud. This video shows like a comparison of using an emulator, how you would type it in the Hewlett-Packard calculator, and they have emulators for like mobile phones. So you could get on your phone a more powerful calculator where you can actually type the equation in graphically and use all of the variables, because when you use the Casio, the entire alphabet's not there. So you can't maybe use the letter F. You'd have to assign it a variable, like I think maybe it's only A through G or something like that. So since it doesn't have the full alphabet, you have to think of substitutions, whereas with this HP calculator, you can see that, let me bring it back up here. I mean, the equation is constructed in the same way on the screen that it looks on the paper, whereas you don't really have to keep track of all the parentheses in the same way that you do with the Casio. So if you're interested to watch this video, I'll put the link online, and you can download an HP50 emulator for your phone. And that's also another way that you can solve the Colebrook equation, is just instead of using Excel and doing it iteratively, the iteration happens inside of the solver. Okay, but there's even an easier way. The Jain equation allows you to solve for the F value directly. And the Colebrook equation was iterative and implicit, but this friction factor formula, the Jain equation, isn't iterative. It has some of the same terms as the Colebrook equation did. It has one term that depends on the relative roughness, and another that's based on the flow conditions. But this is only applicable over a certain range of flow values, whereas the Colebrook equation is broadly applicable depending on, as soon as you're outside of the laminar range, Colebrook works. Jain equation only works for a narrower range of K sub s to D and a narrower range of Reynolds number, but these are usually going to be in the range that you're working in. So this is a pretty useful formula, this Jain equation. So think about that same example we had just a moment ago, and if we want to solve the Jain equation, previously we had a K sub s of 0.15, a diameter of 136 millimeters. The Reynolds number that we got was 1.87 times 10 to the 6th. So here, this is saying let's practice using the Jain equation for this same example. So I'm going to pause for a second and give you a chance. Solve for F using this Jain equation and see how it matches up. Because what we found before when we used the Colebrook, we found it was basically 0.0203. So let's see how close does the Jain equation get in this particular instance to what we had calculated with Colebrook, which we think of as more sophisticated and more accurate. Jain is just an estimate, but it's a pretty good estimate, as you'll see. Okay, so K sub s is 0.15. The diameter is 136. The Reynolds number is 1,872,000. So if we make that substitution into the Jain equation, then get all the parentheses and the exponents in the right spot, I think what I got was 0.0203, which is the same value that we'd gotten from Colebrook equation. The two diverge more the further outside or maybe closer to the border you are on this calibration range. Like, for example, our K sub s to D for this problem is 0.001. So we're right in the middle. We're in a good spot for the K sub s to D. Our Reynolds number in this problem was 1 times 10 to the 6th. So we're in the middle of the Reynolds number range. And so we're in a pretty good zone. But if we were closer to the border of these limits, then there'd be a bigger discrepancy between the Jain equation and the Colebrook equation. Let me show you that substitution again. Did anybody else also get 0.0203? See some heads nodding. That's good. So as it says on the slide, you can use the Jain equation on problems unless I specifically tell you to use the Colebrook equation. And if that's the case, then what you ought to do, if I'm saying to use the Colebrook equation, is show iteration, like the setup of the left-hand side of the equation, the right-hand side of the equation, what the substitutions were, and eventually what you got coming out of that. Or you could just include a spreadsheet setup like this one, but I don't even think that's going to apply. I think we'll just go with the Jain equation. It's a good one. It's accurate. One other approach is the Blasius equation, which only applies when the flow has a Reynolds number up to 100,000. But when that's the case, you can determine the F value based on the Reynolds number. So it's another pretty easy way to calculate the F value if the Reynolds number is 100,000 or less. All right, so that's all we're going to talk about for how to determine the F value, but let's use and apply that in trying to figure out how big should the pipe be if we know the amount of head loss that there's going to be. For example, if water is flowing from a tank to a building, like this is an example that we saw in a previous class meeting, we knew how much head loss there's going to be. Because by definition, the head loss is the amount of energy that there is at the elevated tank upstream minus the amount of energy that is at the point of delivery downstream. So here, the head loss is known to be some value between these 2 points, and so we want to know how big should the pipe be to convey the water that distance. Here it says 250 meters. If we want to deliver the water and provide a certain amount of pressure downstream. So if you know the flow rate that has to be delivered, and you could determine that through like population estimates and per capita estimates of demand of water per person at a certain time. So if you know how much water has to be there, Q, then the diameter of the pipe and its material has to be designed to make sure that you're going to be able to convey a certain amount of flow downstream. So the formula that we've seen for the relation of head loss, H sub F, and the individual pipe characteristics is the Darcy-Weisbach equation. So we're going to rearrange the Darcy-Weisbach equation to go through this process. But here in red, it's asking the question of what's the difference between design and analysis. And I guess one of the ways I describe that is that analysis generally has one right answer, but design can potentially have multiple right answers, depending on how many different parameters are going into the design. Design is iterative, where analysis is sometimes just a once-through process. But in design, you're figuring out how to meet specifications with the available options. So if we want to design the pipe size that's required to deliver a certain flow, this is the Darcy-Weisbach equation, and if we rearrange it for a circular pipe, so this is, assuming that the pipe conduit has some circular profile, and if we're trying to solve for the required diameter, then this is what we end up with. And so the diameter of the pipe that's needed depends on the length of flow between the 2 points and the flow rate, the amount of head loss that's the driving force. So H sub F you can think of as what's pushing the water from one point to another. And then, of course, the G is a constant. Pi comes from the circular shape. When we substitute in the circular shape into this estimation for velocity. So, what we've essentially done is, instead of having the flow velocity, we've substituted in Q. And Q is V is Q divided by area. So if we rearrange the Darcy-Weisbach equation, we can solve for D, the diameter that's needed. But what makes this tricky is that F value isn't just a constant. It's something that changes with respect to flow conditions. And so this is an iterative process because you're going to start with some guess of what diameter is required, and then you're going to check to see what would be the flow conditions for that diameter. And once you know the flow conditions, then you can estimate the F, but then having a different F value is going to change the diameter that's required. So this is a process that has a couple of loops before the solution converges. I'm going to show you what I mean by that. We're going to go through this process of iteratively trying to figure out what size is needed for a certain flow rate, a certain pipe length, and we begin by assuming an F value that would apply, just maybe picking somewhere in the middle of the range, because we don't yet know how rough the pipe is until we know the flow conditions. If you remember back in the Jain equation, what it says about the F value depends on the pipe material, the diameter, and also the Reynolds number. So this process is basically trying to answer how big should a pipe be, but we don't know how big the pipe should be until we know how rough the pipe is, F, but then we don't also know the roughness until we know the flow velocity. So it's an interrelated chicken and the egg question that we have to just assume something to be able to start the process off. So you assume a guess value of the roughness, and then you'd solve for the required diameter using this formula, and then you'd check to see what is the Reynolds number with that diameter, and also then what would be the updated F value. And so that when you have an updated F value, you can put it back into the equation again to find out how that changes the diameter that's required. So anytime you do something iteratively, it can be worthwhile to do it on the computer. And so that's what I'm going to do here is pull up Excel again and go through an example. And if you've got your computer with you, you're welcome to get it out and follow along if you want to go through the same process in Excel. We're going to answer the question of if there's a pipe that is 40 meters long, so that's the physical length of the pipe, and we know that it's made out of cast iron, which we can look up the K sub S of cast iron to be 0.26 millimeters, and we want 300 liters per second to go through it, and then H sub F, the available energy to push the water through that pipe, is 45 meters. So that's the driving force. So we're going to start in this example by just guessing an F value and finding out what diameter would be required if that was the F value that applied. But that guess is never going to be exactly right. So what we'll do after we have a guess F value is we're going to calculate what's the Reynolds number that comes out of this pipe diameter and what's the K sub S to D, and then come up with an updated F value using the Jain equation. And then once we have a new F value, we'll substitute it back into this formula again. So we're going to repeat it over and over again until the F value isn't changing and until the diameter also converges. Okay, so if you're going to follow along with Excel, just start with the blank worksheet. If you're just watching this one, that's totally fine too. I'm going to paste a couple of formulas in here just so that we've got them at the ready. So here's our formula for solving for the diameter. Then I'm also going to paste in the Jain equation because we're going to solve for that a couple of times. I don't need that. All right. So this problem statement says it's a length of 40 meters. What diameter is required? It's cast iron, 300 liters per second. Okay, so here at the top I'm going to put some of the preliminary constants that aren't going to be changing. So for example, our flow rate in terms of cubic meters per second is 0.3 cubic meters per second because the problem statement said 300 liters per second. Okay, the K sub S of the pipe in terms of meters. Now the reason why I'm doing that in terms of meters, even though it gave it to me in millimeters, is that when it goes into the Jain equation, it needs to be in the same units. So if the pipe diameter is going to be in meters, then so should the K sub S value, or I could leave it in millimeters and the diameter would also be calculated in millimeters. But I'll just put this one in meters. So it is 0.15, cast iron, 0.26 millimeters. So 0.26 divided by 1,000. Okay, so that gives me the relative roughness, the equivalent sand roughness in meters. The pipe length, it says, is 40 meters. G, of course, We know the G is 9.81. And the head loss due to pipe friction, that's driving the flow, is 45 meters from the diagram. It said that H sub F is 45. So what that comes from is just maybe the elevation difference between the upstream storage tank and where the water's going to. So this is a known H sub F. And then finally, the kinematic viscosity of water in terms of meters squared per second. And that, as we've already seen once today already, is 1e minus 6. Okay, so those are the constants that aren't going to change. But here is iteration 1, where we start with an assumed F value. So assumed F, let's just pick something in the middle. Like last time what we did was we started with like a really low F value. But that's going to take, if we assume like one of the extremes, it'll take our solution longer to converge than if we take something in the middle. So I'm just going to use 0.015 as the starting F value here. So 0.015. And I'm going to add in the note here, this is a guess. That's not a calculated F value, not yet, because we can't calculate F value. We don't know what is the diameter that's required, and we also don't know what are the flow conditions. Like we don't know the velocity until we know the diameter. So we couldn't calculate an F. We can only guess one so far. Okay, so calculate D. So here I'm going to use this formula to calculate D. Let me move this other one out of the way. So equals 8 times the length of the pipe times Q squared divided by H sub F times G times pi squared Okay, now I need to multiply all of that by F. I should have just maybe had F in this earlier part, but I can do it now. Times this guess F value, and then everything goes to the power of 1/5. Okay, so if that's the F value, then this is saying then the required pipe diameter would be 0.158, and the units there are meters. The diameter of the pipe in meters. Okay, so if that's the diameter, then these are the flow conditions. So, for example, the flow rate in terms of cubic meters per second is going to be the same 0.3 cubic meters per second. I guess I don't need to mention that because it's up at the top. The area of the pipe. So if it was this diameter, then the area of the pipe is pi d squared divided by 4. And then the velocity of flow.
I think you had 2.17 divided by 4.
Thank you for catching that. Pi d squared divided by 4. That's more like it. Thank you. Okay, so then the velocity, I'm going to have this flow rate that's not changing. That's a known flow rate that we want to achieve. Flow rate divided by the area. Okay, so the flow velocity, if that was the pipe diameter, would be 15.25 meters per second. And so then if that's the velocity, then the Reynolds number is going to be velocity times diameter divided by kinematic viscosity. So that's the function for the Reynolds number. Okay, so now we can determine a new updated F value. So updated F value. And now we're going to use the Jain equation to calculate an updated F value. So 1.325 divided by the logarithm of k sub s divided by 3.7 divided by d. Okay, so that's one side of the equation. Then the other one here, 5.74 divided by the Reynolds number to the power of 0.9. And then all of that has to be squared. Easy to lose track of this squared term at our peril. So we have to ask ourselves, is this f value like in a reasonable range? It is. So our initial guess was that the f value should be 0.015, and we have an updated f value of 0.0224. Okay? So now that we have a new f value, this was iteration 1. Now we're going to do iteration 2. The reason why we're continuing, why we haven't stopped at iteration 1, is the f value changed, and so we haven't yet converged. If the f value is changing within a step, then that tells you that you need to keep going in your calculations. And also, what we're going to do is we're going to compare in iteration 2, we're going to look at how is the new diameter compared to the one from the previous iteration. And when the f value is no longer changing and the diameter is no longer changing, that's how we know that we can stop our iterations and that we've converged on the correct solution. Okay, so iteration 2. We no longer have an assumed f value. We're going to use f value from the previous step. So the previous f value that we calculated was this updated one. Okay, so we've got that. Calculate d in terms of meters. Now let me see if I'm sneaky here. If I can, instead of having to type that equation in again, I'm just going to copy and paste. This is the nice thing about Excel, is once you set up a formula, you usually don't have to type it in again. So I'm going to do here copy, and then down here click on paste, and I got to make sure there must be something that's not anchored right. We've got to make sure it's looking in the right spots. Okay, so 8 times the length, and then it's looking at the flow rate. It's the flow rate that I didn't anchor. So it should be this, should be looking up. Let me go back into here. Maybe what's easiest for me to do is just fix this formula for the D. All right, so here's my D formula. I need to anchor this reference to the flow rate, B1. So I think as long as I've got that anchored, maybe I can copy and paste it now. So copy and paste. It looks like it worked. Let's make sure that it's looking up at all of these constants that don't change, and then the one thing that is updating is it's looking in the new spot for the f value. Okay, so this is saying if your f value is 0.0224, then this is the required diameter. And we can copy all of this as well, Control C, Control V. So this is going to tell me what's the area of that new diameter, what would be the velocity for that area, and the flow rate that doesn't change. What's the new Reynolds number based on the new velocity, our D value that's calculated, and then our updated F value. Looks like something isn't quite right there. It's looking in the wrong area. So let me anchor the reference to the correct spot for K sub S. I should have anchored it before, but I think that's the only one. Okay, so copy, Control C, paste, Control V. All right. So let's look and see how did things change in the first iteration compared to the second. So it went from 0.015 to 0.224. That's a big change. But then within this iteration, it went from 0.0224 to 0.0219. So that's a relatively minor change there. It's not changing a lot. So we're getting close to convergence. And the diameter in the second iteration was saying, no, it's not really 0.15. It's more like 0.17 that's required. So now I'm going to say iteration 3. underline that. Okay, now I'm going to copy all of this and copy and paste. And it's going to use relative references where the F value, it's looking at the previous one. The diameter is just using this new F value that we've calculated at the end of iteration 2. So how did the diameter change from 0.171 to 0.171? I'd say that's pretty stable. Like if we just round that off to the nearest thousandth of a meter, it's pretty close. And how does the F value change within the iteration? 0.0219 to 0.0220. So just for kicks, let me do a fourth iteration, even though we've basically got our answer. I'm going to say iteration 4, because at this point, all I have to do is copy and paste. It's no extra work on my part. I'm just highlighting this, copy and paste, and now it's not really changing at all. The diameter here, 0.1707, is the same as what we'd gotten in the previous example. The F value in and the F value out is the same. And so our final answer, the required pipe diameter is 0.1707 meters. Now that's the pipe diameter that's needed for like exactly meeting the requirements. But like if you can't buy a pipe that's that size, then should we go smaller or go larger? Go larger. Yeah, because what we'd want to do is we'd want to provide at least enough flow downstream. So let's say maybe a 200 millimeter pipe is available. We'd get a 200 millimeter pipe, and then we'd put a valve upstream of it so that we could open and close the flow appropriately. All right, so any questions on that example where we were solving for the required pipe diameter? All right. I didn't take roll at the beginning of class, so let me do that now.